we can still keep up. Please go on with your talk.
Okay, hello everyone. So I'm so sorry about this malfunction with the earphone. I guess it happens many times from the others as well. So I'm Kaiqiang Lin from University of Regensburg in Germany. So first of all, it's a great pleasure to participate in this conference. In the following, I would like to try to contribute further to a diversity of this conference by introducing our recent progress on this excitonic quantum inference in 2D semiconductor. So as introduced by several speakers before already, we know that in monolinear TMDC system, it's a direct bandgap semiconductor. If you shine light onto the material, you can excite the electron from valence band to conduction band. It gives you this informal exciton. It gives you this two-level system, which already shows strong light matter interaction. But if we look closer into the band structure, we will notice that the light can further excite the electron from first conduction band to high line conduction band, which give you a three-level system instead. And from AMO physics and quantum optics, we know that the three-level system in atoms are a basic building block for wonderful quantum interference phenomena such as electromagnetically induced transparency or slow light or lasing without inversion. So for those ones who might not be very familiar with the electromagnetically induced transparency, I will give a very brief background. So assuming there's a bunch of cloud, atom cloud has this three-level system. If you measure the transmission, you get this Lorentzian peak around 1 to 2 transition frequency. And now if you shine a lot of laser control beam couples 2 to 3 transition, and then suddenly the original non-transmissive frequency will start to be transmissive. And this can be understood as the laser couples 2 to 3 transition dress the second state and give you this dresser state and make the original absorb the transmission frequency non-absorbable anymore. So the question now is whether we can truly see this in a monolinear transition method dichotomized system. So instead of measuring it with absorption or transmission, we instead measure with a second harmonic generations, which is much more sensitive than the absorption. So in general, second harmonic generation will give you this Gaussian peak, which represents the input pulse duration, which here we use 80 femtosecond laser. And indeed, in monolinear tungsten diselenide system, at the same frequency, we can see a transparency dip in the second harmonic generation spectrum. And this is not trivial. So this splitting only happens at a specific wavelength. If we do an excitation wavelength dependence, as you can see here, at a higher energy, you got Gaussian peak, and then at around 724, you got a splitting, a transparency dip in the second harmonic, and if you go further, you recover this Gaussian peak again, and the whole spectrum appears as anti-crossing behavior. And this is a normalized second harmonic intensity. If we now look at the second harmonic efficiency, which is absolute intensity, and then you can see that indeed there's a minimum second harmonic efficiency as well at this specific wavelength exactly, you can get this splitting behavior. And so the transparency appears in both the second harmonic emission and also the excitation spectrum. And now the question is, how do we simulate the system to gain further insight into the system? So we know that for second harmonic generation or Chi2 process, it's a Chi2 process. We just go to a textbook, get this Chi2 function, but this is only limited to the perturbative situation. So for non-perturbative situation, we took the approach from using this density matrix formalism. So this is a method commonly used in quantum optics or atomic gas system. So we calculated time-dependent polarization from the density matrix, which the time of evolution comes from this Lindbergh platform. And this is the electric field, and this term is the transition dipole term, which couples the states. And this is a dissipation term, this is a repopulation term. From there, we can do a Fourier transform from the time-dependent polarization to the frequency domain. We can get a second harmonic. By looking at the 2 omega frequency, we can get a second harmonic generation. And with the surprisingly, with the 3-level system, we can immediately reproduce what we can see in the experiment appearing as an anti-crossing behavior. And with that in hand, we can now look into how the density matrix dynamics works in this in the system. So for a trivial case, the laser beam comes in, excites an electron from ground state to a second, to a third, and then this will come back again. This is a trivial case. So here, when the splitting occurs, if we look at the density matrix dynamics, we will find that it will excite an electron from ground state to second, to third, and then the laser will drive the electron backwards from third state to a second state, which interfere with the incoming light, the 1 to 2 transition, and give you this transparent state. And this oscillation appears as here, oscillation in the density of second state, as you can see here. And we know that 2 to 3 back to 2 transition corresponds to 1 Rabi cycle. We know Rabi's frequency is proportional to the electric field you apply to the system. And then we can imagine if we increase pulse energy, we can increase the Rabi frequency. And as you can see here, indeed, if we increase the pulse energy, we can see 2 Rabi cycle within this pulse duration. And this gives you the 2 dip in the second harmonic generation spectrum. And so the number of second harmonic dips equals to the number of Rabi cycle happens inside single pulse duration. And this is truly what we can observe in the experiment by increasing pulse energy. And there's a minor difference between these 2 simulated and the experimental one. This corresponds to many body effect, which was not included previously in the density matrix dynamics or calculation. If we adjust parameter, we can reproduce what we can see in the experiment. So similarly, there's another approach to include more Rabi cycle by increasing the pulse length, because by increasing pulse length, we can increase the pulse observation window. So without increasing the Rabi frequency, we can observe more Rabi cycle if we increase pulse duration. And we can see 2 dips as well inside a single second harmonic spectrum. So this is exactly what we can improve in the experiment by switching the laser from 80 femtosecond to 140 femtosecond with the same pulse duration, same pulse energy. We can see a dip number increases actually. So far so good. So but still there are many questions left. For example, people will ask, okay, what's the merit of the Excitonic 3-level system compared with atom? Because in atoms, we know that the coherence time can go up to a second. And especially also, is this phenomenon truly general? Especially considering this in monolinear monolinear diselenide system, you don't see a quantum interference at all across a very broad range. So in the following, I would like to try to answer this question by showing you the tuning of the excitonic state and control of the quantum interference. Because in atoms, we know that the state energy are given by the nature. We cannot really tune it. But in excitonic system, we can tune it in many different approaches. So the first approach we thought of is just doing dielectric tuning by capping the mononaire with a different polymer or boron nitride, and then we can tune the dielectric environment, and you can shift the state energy by 50 MeV. But this is not enough. So this is not enough to turn off, break the degeneracy to turn off the quantum interference. So we need to find another more efficient approach to tune the system, which is the twist angle control. I will show you later here. So if we look at the band structure of this three-level system, we will find that for the first conduction band, the electronic state are mostly localized at the tungsten atom in the middle of this three-atom sandwich. But if we look at the high-lying conduction band, we will see that the electronic state no longer localized around the tungsten atom in the middle of this three-atom sandwich. It extended further to the selenium atoms as well, which means when we stack two monolayers together and place a twist, the first conduction band electronic state wouldn't be so sensitive to that. But for a high-lying conduction band, you'll be very sensitive to twist due to the hybridization. So then to prove this idea, we measure first the A exciton from the first conduction band. As you can see here, it shifts by 24 MeV, which is very small. But if we look at the high-lying conduction band, you will see that this excitonic state shifts by more than 200 MeV across from 0 degree to 30 degree, let's say, and then it will shift back when we tune to 59 degree. And this gives us a highest twist angle susceptibility so far, so which is 8.1 MeV per degree. And if we look at the A exciton, it's just 0.1 MeV per degree, and for the indirect exciton, it's 3, and interlayer exciton is even smaller. And this gives us another alternative way to determine the twist angle. With this in hand, we can imagine that when we do the twist angle, because the second state is fixed, but we tune the third state around. And then if we break the degeneracy, we will lose the quantum interference, as you can see here in the simulation. But this is an experiment. Indeed, in around 0 degree, we don't see the quantum interference. Basically anti-crossing here. And starting from 21 degree, we will start to see this anti-crossing, and until 45 degree. And then if we go further to close to 60 degree, you lose the quantum interference again. If we summarize this phenomena here, this is twice the A exciton energy, or the second state energy. And this is the blue one corresponds to the emission of the from a high-lying exciton, and the yellow one corresponds to the anti-crossing dip position, marks where the third state is. As you can see, when the third state is closer to the twice of A second state energy, then quantum interference occurs. When you tune it far away, then you don't see this. So then it brings back to the question whether we can achieve this control in monolayer MOSC2 as well, because in monolayer MOSC2 we don't see the quantum interference, and we propose that because because the third state is much higher than the twice of 1 to 2 transition. So then we can imagine at a 0 degree angle, we tune the third state to the lowest. So we fabricate this twisted bilayer MOSC2 at around 0 degree, and indeed we can recover this quantum interference phenomena in MOSC2. And as you can see, truly, in this, the nonlinear property of the system can be controlled by the twist angle. And we know previously that from literature, the second harmonic in general is governed by the inversion symmetry. And for 0 degree inversion symmetry is broken, you have the highest second harmonic, and it drops monotonically to 60 degree, because in 60 degree you have an inversion symmetry. But if we examine it, look at it carefully, we will notice this is not as simple as that, because the whole dispersion of the Chi2 function will be changed by twist angle due to the band hybridization between two adjacent layers. And also the excitonic state will shift, and quantum interference occurs and turn on or off. So as you can see, even at a certain excitation energy, this 21 degree Chi2 can be even higher than 1 degree, which is not obvious before. So with that, I would like to conclude my talk. I hope I have convinced you that there's truly a 3-level system intrinsic to monolinear TMDC system, and we can visualize this Rabi cycle in a system through second harmonic generation spectrum, and the quantum inference phenomenon can be controlled by the twist angle, and we consider this might bring us a new possibility in this solid-state quantum nonlinear optics, especially in optical wave mixing or building optoelectronic device, exploring this quantum inference phenomena. And I would like to thank the student Robert Martin, Jonas Bauer, and my colleague Sebastian Banger, John Lupton, and the collaborators from Regensburg and Cambridge, and funding from DFG. And thank you for your attention. I'm looking forward to questions.
Well, thank you very much. I think we have time just for one small question, because we would like to keep up with the schedule. So please, if there is a question, raise your hand and ask rapidly. Yes, Alexander, please.
Yeah, I can ask rapidly. The question is it true that for the second band in the conduction band, you have a negative effective mass?
Exactly, yes, that's a very good question actually, but I don't think we can have a very fast answer. So this is a very nice, because this is, but I can show you this is another paper we are preparing. So it indeed is a negative mass. So in general, people consider the exciton wouldn't form if the electron has a negative mass, right? Because the electron will accelerate away from the hole. But this is not necessarily the case if the electron is heavy enough. If it's a heavy enough electron, the light hole can trace and trap the electron in the middle. So it can orbit like a co-orbiting system. So it can, if you calculate DFT as well, you can see this exciton as well from this band. So together with the Steve Louis group in Berkeley, we calculated this exciton, and they calculated an exciton, and this exciton features a strong phonon progression, as you can see here, because it tends to scatter downwards and resonantly with the K prime value, and then give you this 10 phonon progressions peaks. Yeah.
And my question was, does it change also the interference effect that it has negative mass, or it's just technicality?
Aha. So far, no, I don't think so, because in the quantum interference phenomena, it happens at 100 femtosecond. So, which means the phonon, electron phonon coupling or scattering rate here, we consider is around also 100 femtosecond time scale. So at least for a moment, we don't see this affecting our this system, actually, yeah.
Thank you, but if I have questions, I should ask later, yeah.
Thank you very much. Thanks for this interesting discussion. Now let's move on as fast as we can. So please, the next speaker is